Somewhere in a hospital right now, a heart monitor flatlines. For the next few seconds, and only the next few seconds, the person lying there is not yet gone in any way you'd recognize. Their skin is still warm. Their hair hasn't caught up to the news yet. And deep inside their skull, encased in bone and bathed in fluid, their brain is not simply switching off like a light. It's doing something else entirely, something scientists only started to understand in the last 2 decades, using equipment wired directly into the brains of dying patients who agreed, in their final days, to let researchers watch. What that equipment recorded would upend a century of assumptions about what death actually looks like from the inside. But to understand why it's so strange, you first have to understand what dead really means, because clinically, it isn't one moment. It's a process. And that process starts with a countdown nobody can stop. Doctors actually split death into stages, and the gap between the first stage and the last can stretch from minutes to days. The first stage is clinical death. The heart stops pumping, blood stops circulating, breathing ceases. For most of human history, that was the end of the conversation. No pulse meant no chance. But clinical death is reversible, at least for a while, which is exactly why CPR and defibrillators exist at all. The real deadline is set by your brain, and specifically by its refusal to store energy for later. Unlike muscle, which can coast for a while on stored glycogen, neurons need a constant, uninterrupted supply of oxygen and glucose, delivered fresh every second by blood flow. Cut that off, and the countdown to permanent, irreversible brain death, the final stage, begins immediately. Doctors have long used a rough rule of thumb, somewhere between 4 and 6 minutes without circulation, and the risk of lasting damage climbs sharply. The moment blood stops moving, every cell in your body switches from a 5-star kitchen to emergency rationing. Cells normally burn oxygen to make ATP, the molecule that powers essentially everything a cell does. Without fresh oxygen, they fall back on anaerobic metabolism, a backup generator that burns glucose without oxygen and produces a fraction of the energy, along with a buildup of lactic acid. It's the same emergency system your muscles use during an all-out sprint, which is why they burn afterward, except now the entire body is sprinting with no finish line. Within minutes, the tiny pumps in each cell membrane that keep sodium out and potassium in start failing for lack of fuel. Water follows the imbalance, and cells begin swelling from the inside, a process doctors call cytotoxic edema. In the brain, this is catastrophic, because the skull is a fixed box with nowhere to expand into. But here's what surprised researchers once they started monitoring brain activity during this exact window: the brain doesn't fade out quietly while all this happens. In some cases, it appears to do almost the opposite. Long before anyone studied brainwaves directly, doctors and hospice nurses noticed something consistent: patients seemed to keep responding to voices in the room long after they'd stopped responding to almost anything else. Sight goes early, pupils lose their reflexes, and the visual cortex, an energy-hungry piece of real estate, is one of the first regions to go quiet. Touch and smell fade next. Hearing is different, because the auditory system needs comparatively little oxygenated blood to keep firing, and the regions that process sound sit deep and well supplied. A 2020 study out of the University of British Columbia, using EEG on hospice patients in their final hours, found that some unresponsive, actively dying patients still showed measurable brain responses to unexpected sounds played in the room, not full comprehension necessarily, but a working auditory system registering that something happened. It's part of why nurses have quietly told families for generations to keep talking, even after a patient stops answering. Hearing may genuinely be one of the last things to go, a detail equal parts comforting and unsettling, depending on what you think the person on the bed can still take in. While all of this unfolds internally, the body starts broadcasting the process outward, in stages forensic scientists have used for over a century to estimate time of death. First comes rigor mortis, the body cooling toward room temperature, roughly 1.5 degrees Fahrenheit per hour at first, though the rate depends heavily on body size and surroundings. Then rigor mortis, with the heart no longer pumping, blood stops fighting gravity and pools in the lowest points of the body, staining the skin a deep purplish red within 30 minutes to 2 hours, a pattern investigators use to tell if a body has been moved. Finally, most famously, comes rigor mortis, the stiffening people associate with death scenes in movies. It isn't muscles seizing up dramatically. It's chemistry. Muscle fibers need ATP to release the bond between two proteins, actin and myosin, after every contraction, including the microscopic ones that maintain resting muscle tone. Once ATP production stops for good, that bond locks in place, frozen mid-contraction, typically starting 2 to 6 hours after death and peaking around 12. The classic pose of death is really just a muscle stuck mid-flex, waiting on a fuel delivery that's never coming. And the same cells doing this locking are already beginning to digest themselves. That self-digestion is called autolysis, and it's driven by the body's own enzymes. Without oxygen, cells can't maintain the membranes that normally keep digestive enzymes safely locked inside compartments called lysosomes. Those membranes break down, the enzymes leak out, and they start dissolving the cell from within, the body eating itself with tools it always carried, just never let off the leash. Around the same time, the trillions of bacteria living peacefully in your gut lose the immune system and oxygen levels that kept them in check, and with nothing holding them back, they begin consuming the body itself, spreading outward through the bloodstream and producing gases like methane and hydrogen sulfide as they go. Forensic anthropologists studying this process at outdoor research facilities, sometimes nicknamed body farms, have documented the whole sequence against temperature, humidity, and insect activity to help investigators pin down time of death in real criminal cases. It's grim, methodical, and almost entirely predictable. Which makes what happens in the brain, in the opposite direction of all that decay, even harder to explain. For as long as people have been resuscitated, some have come back with stories, a sensation of leaving the body, a tunnel of light, an overwhelming calm, sometimes vivid memories replaying at high speed. For decades, doctors filed these near-death experiences under interesting anecdote, rather than serious science, largely because there was no way to check what a supposedly flatlined brain was actually doing while the story unfolded. Then, starting with a 2013 study on rats and eventually extending to monitored human patients, researchers got direct EEG recordings from brains in the exact window between the heart stopping and the brain shutting down for good. What showed up on those recordings did not look like a brain running out of steam at all. In 2013, University of Michigan neuroscientist Jima Borjijan led a study, published in the Proceedings of the National Academy of Sciences, recording brain activity in rats during cardiac arrest. Instead of a steady decline, the researchers found a sharp spike in high-frequency gamma waves, the pattern associated with focused, conscious awareness in a fully alert brain, within the first 30 seconds after the heart stopped, at levels higher than anything measured while the animals were awake. Nearly a decade later, Borjijan's team got an extraordinary, unplanned chance to check whether something similar happens in people. In a widely discussed 2023 case study, doctors were monitoring the brain activity of an elderly patient in cardiac arrest whose family had chosen to withdraw life support. As the patient's heart stopped, the EEG recorded a comparable surge, a burst of gamma activity, along with a spike in connectivity between regions tied to memory, sensory perception, and what scientists call the brain's hot zone for conscious experience. Researchers are careful not to overclaim, this was a single documented case, and scientists still debate what, if anything, a person feels during that surge. But the finding itself was undeniable. For a brief window, in the exact moment it's supposed to be failing, the brain doesn't quiet down. It appears to organize itself into one last, strangely coherent storm. So what really happens in the final seconds after you die? Not a light switching off, and not the peaceful fade culture often imagines either. It's a cascade, cells rationing energy, senses shutting down in a specific order, hearing holding on the longest, chemistry locking your muscles in place, and somewhere inside that shutdown, in at least some documented cases, a final surge of organized brain activity that looks less like an ending and more like one last effort to make sense of everything at once. Nobody can tell you with certainty what, if anything, is experienced in that surge. But the data suggests the brain doesn't go gently. Whatever dying is, it turns out to be one of the most active things the human body ever does. If a relative or a doctor has ever told you a story about someone's final moments that didn't match what you expected, we'd genuinely like to hear it in the comments. Accounts like those are part of what pushed researchers to start asking these questions in the first place.